Hi everyone, welcome to our live stream for the Chemistry Paper 1 exam. So goal for tonight is to go through everything on C1, C2 and C3 for the OCR Gateway course. So that's both combined and the triple chemistry higher foundation. For those of you that do AQA, there is a lot of overlap between these. So what you'll find is that a lot of the topics that you'll be doing are exactly the same, because at the end of the day, an atom is an atom. So to start off with then, we're going to have a little look at C1. So the first thing you should have looked at were the ideas about particles. So hopefully we know that one of the key things about chemistry is that we use something called the particle model. Now, the whole idea of models in science is that we can use them to solve problems, because we can't always physically look at the things because sometimes they're incredibly tiny. So we can use a model to then help us to understand it. So that means we can then make some predictions and develop a greater scientific understanding about these concepts. Now, in terms of the particle model, this is all about describing the arrangement of particles and how they move in the different states of matter. So what we can actually do is use the particle model to then explain certain properties of that substance. So what we actually find here is we can explain things like the ability to compress a gas, because we've got all of that space between the particles, but you can't compress a solid because there's no space between them, so there's nowhere for them to go. You can also explain that solids can't flow because those particles are all held in a very fixed shape and they can only vibrate around a fixed point, whereas something like a liquid or a gas, they can flow because the particles are free to move over each other. So when we're thinking about the particle model then, what we actually have are these three little diagrams that you probably learned all the way back in about year 7. So you've got your solid, first of all of the particles in nice neat rows, all touching. Your liquid is where they're touching. There's a couple of little gaps between them, but not giant gaps. But you can see they're not arranged in these lovely regimented rows. And then we've got the gas on the far end where they're all really spaced out, not touching each other. So that's what we're talking about with the particle model for solids, liquids, and gases. So what we're actually thinking about in terms of the arrangement of the particles, there's two words you really should know on this one. Either that they're regular in their arrangement or they're random in their arrangement. So what we find is that the solid, they have a regular arrangement, whereas liquids and gases, it's a random arrangement there. You might also be asked about the relative distances between those particles. So what we can actually see is that starting with the solid, they're really close. By the liquid, they're still close, but not as close as in the solid. And by the time we're in the gas, then they're really far apart from one another. In terms of the movement of those particles, solids, they only vibrate around a fixed point. Our liquids, they're able to move around each other. And in the gas, they're zipping all over the shop really quickly in all directions. One thing that they could ask you to do is to talk about one of the problems of representing particles in a 3D model. So where you draw all your little particles as the circles in that 3-dimensional shape. And the key thing here is the fact that when we're looking at that, we can't see all of those particles. You can only see the ones on the front face, the top, and one of the sides. All of the others are hidden from view, either fully or partially. So that's one of those limitations that we've got there. The next thing we need to consider are the types of changes that we could see. And again, I'm hoping this is something that you did back in Key Stage 3. So you've either got physical changes or you've got chemical changes. So a physical change, first of all, is just a change in the state of matter. So this quite simply is where we've got something melting, you've got something dissolving. Those are physical changes. And what we can do is we can identify them because they tend to be reversible, first of all. So we can always change water back into ice and no new substance is made. If we start off with H2O in ice, then we've still got H2O in its liquid form as well. So the chemical isn't changing. If we think about the chemical change then, this is where we've got a change that produces one or more new substances. So what we find here is these are the ones that tend to be irreversible. So you can't change them back to what we started with. Now, what we also find is that the properties of that product tend to be quite different to that of the reactants. So just bear in mind the difference between chemical and physical changes. Physical, change of state of matter; chemical, new substances are made. What we find in terms of the particles when we think about these is that in the physical change, then the particles stay the same. It's just their arrangement and how they move that changes. Whereas if we consider the chemical change, then the particles are actually physically breaking apart from one another, and then they rejoin in a new combination. So make sure you can actually work out the difference between chemical and physical changes there. For those of you doing the higher tier, then you do need to know some of the limitations of our particle model. So quite simply, when we're thinking about the particle model, there's three key limitations about it, three things it doesn't really take into consideration. The first one is that it doesn't take into consideration any of the forces between the particles. The second one is that the size of the particles is just disregarded. They're all treated as one and the same. And the third one is we don't really think about the space between particles properly. So those are three of our limitations there of the particle model, but we still use it because it's still a good guide to how things actually work. Everyone, again, so that's combined the chemistry, higher and foundation. Then we need to know about the structure of an atom. But before we can really get into that, there's a few key words that we frequently mix up or don't really understand that we really need to know for this. So our first one is the term element, which quite simply is a substance whose atoms all have the same atomic number. An atom is just the smallest particle of any element, and a molecule then is a particle consisting of two or more atoms that have been chemically joined together by those things called bonds. When we're thinking about the size of an atom, we generally give that as the atomic radius. And hopefully we know from our maths that when we're talking about a radius, that's half of the diameter. So where we're drawing it as a circle, all the way across is the diameter, halfway, that's the radius. And what we then also need to know is that when we're thinking about that atomic radius, then typically we refer to that as 0.1 nanometers. Or if you prefer, 10 to the power minus 10 meters. So you do need to know the size there, but the good news is that the atomic radii size and the bond lengths are both the same. So if you get a question asking you about the size of an atomic radius or the size of a typical bond, then just go with 0.1 nanometers or 10 to the power minus 10 meters, depending on which way they phrased it in the question. When we think about the actual atom and its structure, this should be the diagram you're all really familiar with. So what we've got in the center is the nucleus, which is made up of the protons and the neutrons. So the protons, the blue ones with the plus, the neutrons, the red ones with nothing. And then we've got these shells or orbitals around it that contain the electrons, the green ones with a minus in there. So we do need to know that basic structure because in the past, they've actually put on one of the little diagrams with a little label saying, what is X? And you need to be able to label it. So we've got the nucleus in the middle, which is protons and neutrons, and then the orbitals or shells around the outside, which contain the electrons. The other favorite question of the past was always looking at the subatomic particles, their relative mass and their relative charges. So what we actually find is you need to know that for the protons, the neutrons, and the electrons. So in terms of our proton, its relative mass is 1, and its relative charge is +1. The neutron has a relative mass of 1 and a relative charge nothing, it's neutral, therefore it's 0. And the electron has a relative mass of 0.0005 and its relative charge is -1. So remember, proton positive +1, electron is a negative -1. So do make sure that you know those because they have given you that little table with a few blank spaces before and expected you to be able to fill it in. In terms of another couple of important terms you need to know, there's 2 on the periodic table. And do remember that in your exam tomorrow, you will get a periodic table as part of your exam. So you don't have to memorize all this stuff. It's there and given to you. Now, what you actually find is you've got the atomic number and the mass number on that periodic table. So the atomic number just tells you how many protons or how many electrons there are, because in an atom, they're the same. And your mass number is the number of protons plus the number of neutrons. So from those two numbers, you can work out how many protons, electrons, and neutrons there are in any element at all on the periodic table. So all you actually need to do there, if they ask you to work out how many neutrons there are, is your mass number minus the atomic number. If they ask you how many protons there are, just look at the atomic number and write it down. If they ask you how many electrons there are, just write down the atomic number again. The only one to watch out for with this is if they've got ions. So ions are those charged particles, which hopefully you remember, and therefore they're not neutral atoms. So your number of electrons is going to be different. It's only the electrons that will change. It's not going to be your protons. So just watch out for that one. Another key term we should know is the word isotope, which quite simply is an element with the same number of protons and electrons, but a different number of neutrons. So that means our atomic number is going to be the same, but the mass number is going to be different. So make sure you know that definition, because that used to be one of their old favorites. If we go back to thinking about the ions for a moment, then they're charged particles, as we've already said. So what we find is they're either going to have a positive charge or a negative charge. So what we actually find is that the electrons being gained will make the ion have a negative charge, whereas the electrons being lost will make it have a positive charge. Because if you lose electrons, which are the negative subatomic particles, there's more positives than negatives, and vice versa. So obviously make sure you can talk about that one. So what we're actually looking at in terms of the atom is something that came up over a long period of time. This wasn't something that a scientist woke up one day and came up and said, that's it, this is the atom. It's something that took a long time for us to get to where we are now. So what we actually have are 4 key scientists for OCR, 5 if you do AQA, that you need to know. So the first scientist is John Dalton. So back in 1803, he came up with this idea that all matter is made of atoms, and that all of these atoms of an element are identical to each other. So he then went on to say, even though all of those atoms in an element are identical, different elements will contain different types of atom. And he described them as these tiny indestructible spheres. So that's where we get the idea of that little ball. The next scientist that really had a big contribution is in 1897 with J.J. Thomson. And his big thing was he discovered the electron. So he carried out these experiments using cathode rays. And those beams that the cathode rays actually were actually made up of negative particles. And he worked that out because as he fired those beams into these magnetic or electric fields, then they changed direction. So he said they must be negative to do that. And that's where he got the idea of the electron. In order to make this work and have these neutral things overall, he came up with this idea of the plum pudding model. So that's where we've got this positive cloud with these little negative electrons scattered through it, much like plum puddings back in the day. Our next scientist that we come on to is Ernest Rutherford. So we're jumping forward to 1909 at this point. Now, Rutherford actually worked alongside 2 other scientists, which were Geiger and Marsden. And what they did was an experiment using these really thin sheets of gold foil. And they fired these positively charged particles called alpha particles at the gold foil. Now, the idea was if the plum pudding model was right, then they would just go straight through because this positive cloud had no substance to it. So they'd just be able to go right through. But they didn't. What they actually found was some of those alpha particles bounced off and even reflected straight back. So what we actually find is that they said this plum pudding model doesn't work. So he said that we must have a positive nucleus in the center there. And that nucleus must contain most of the atom's mass. And therefore, the electrons are going to orbit kind of like the planets in our solar system. It was in 1913 that we then come up to our 4th and final scientist for OCR, which is Niels Bohr. And he basically used a whole load of really complex mathematical models that we don't need to worry about, in order to show that these electrons occupy fixed energy levels or shells around that nucleus. You don't need to know the years. That's just there to give you a bit of a timeline as to how long this took. So we can see it's over 100 years to get the idea of the atom here. If you do AQA, then you do need to know about Chadwick. And Chadwick's great contribution was he discovered the neutron. So let's hope that if that comes up this year as it did last year, you don't all take to Twitter in a rage not having heard about Chadwick. So that was C1. All you had to do was learn about atoms and their structure there. C2 then, our first thing we need to know about is the relative atomic mass. So what we're actually looking at here then is when we think about an atomic mass, we're not just going to put it in grams. That would be just ridiculous. You'd have so many zeros after the decimal place, it would always be wrong because you'd always miscount. So we use a relative atomic mass because what we're actually doing there is we're comparing it to something that's about that same size. And what it actually is the mean mass of an atom of an element compared to 1/12 the mass of an atom of carbon-12. Bit of a mouthful, but that's the definition you need to know. So relative atomic mass, the mean mass of an atom of an element compared to 1/12 the mass of an atom of carbon-12. If we're talking about the relative formula mass, then that's the mean mass of a unit of a substance compared to 1/12 the mass of carbon-12 atom again, okay? Now, just remember that we've got those. If you're talking relative atomic mass, get the periodic table. It's the big number in the box. Dead easy. If you're talking about the relative formula mass, then obviously you've got to add up those relative atomic masses from the periodic table in the chemical formula. So if we had CO2, which is carbon dioxide, then carbon has a relative atomic mass of 12, oxygen has a relative atomic mass of 16, so 2 times 16 is 32, plus our 12 gives us 44. That's the relative formula mass. So just make sure you can work those out, but it's basically adding. And as always in science, you are allowed a calculator, so you don't have to use your brain cells to add up in there. You can literally get your calculator and type it all in to make sure you get it. The next kind of formula we need to know about is one called the empirical formula. Now, empirical formula, quite simply, is the simplest whole number ratio of the atoms that we find within a compound. So if we had something like C4H10, for example, then to work out the empirical formula, you use the highest common factor of both 4 and 10. So in that case, the highest common factor is 2. So 4 divided by 2 is 2, and 10 divided by 2 is 5. So our empirical formula is C2H5. So all you do, find the highest common factor, and then just divide each of those particular atoms by that number, and then you can work it out. The next thing we need to come on to are pure and impure substances. So what we actually find is a pure substance will consist of only one element or compound. So pure substances only have one element or compound, whereas an impure substance is one that's going to contain more than one element or compound. Pretty straightforward. If we're talking about a mixture, then that's where we've got more than one element or compound that are mixed together, but they're not chemically bonded. So they're just floating around in the same area, the same fluid, but they're not actually physically joined together by a chemical bond there. Good example of that would be the air you're currently breathing in. So that's a mixture. In the air you're breathing in, you've got oxygen, nitrogen, carbon dioxide, random other gases, but they're not bonded together. Another kind of chemical we need to know about is something called an alloy. So when we're talking about alloys, then this is where we've got a mixture of one metal and one or more other elements. So it is a mixture, but one of those is a metal there. Now, in terms of how we can work out if something is pure or not, then what we actually have is the idea of the melting point. So melting point, quite simply, is just the temperature at which it changes from solid to a liquid. And if it's a pure substance, that occurs at one single temperature. So if it's an impure substance, then it's not going to melt at just one temperature. It's going to do so over a range of temperatures. So that's one quick way you can identify if a substance is pure or not, is to actually test the melting point. If it all melts at one temperature, it's pure. If it's over a range, it's impure. And the greater that difference in temperature over which it melts, then the lower the purity of it will actually be. What we do to work out the melting point might seem really obvious. You heat it up, because obviously to melt something, you've got to increase the temperature there. And then you just record the temperature at which it melts, and then you can plot it on a nice little graph to work it out. Two key things about this though. First of all is heat the substance slowly. You're not going to whack a Bunsen burner on a roaring flame and then try and guess at what temperature it actually melted. That's going to be no use to you at all. You need to increase that temperature really slowly so that the whole substance will increase in temperature. Secondly, you need to stir the substance as it melts. That means that the whole sample is at the right temperature and you don't get any little hot spots in there. The next thing we're going to come on to are the separating techniques. Now, separating techniques are actually one of those potential assessed practicals. And it's not really just one practical. We've got all of these different separating techniques could come into this. So just make sure that you're really good at these, because we know they're going to ask you questions on these assessed practicals. We just can't say which ones. First thing, we need to know some key terms. So solution, quite simply, is the solute, which is the solid dissolved in the solvent. The solvent is the liquid that does the dissolving. The solute is the solid that dissolves. If something's soluble, it will dissolve. If it's insoluble, it doesn't dissolve. So make sure you know those 5 key terms first of all. The first separating technique we're going to look at then is filtration. So this hopefully is our filtration reminder. You should have done this in class. You probably did a really exciting experiment where you had some muddy water and you sat and watched it slowly drip through the bit of filter paper. So what we've got, a funnel at the top here with a bit of filter paper in there, and we sit it in a conical flask. So you pour your mixture up at the top here, and then only the solution called the filtrate will come through. Any of the larger solid particles actually sit up here, and they're called the residue. One of the things we do is we flute the filter paper. So you don't just fold it into 4, as we do in class quite frequently. You're meant to fold it into this lovely fluted shape, because then you've got a lovely big surface area to make it way more efficient than the really sad slow drip that we normally have. So make sure you can label your bit of filtration equipment there. In terms of how this actually works, then we're going to use this to separate an insoluble solid, so one that doesn't dissolve, from a liquid. And the whole reason that this works is because the bit of filter paper itself has these teeny tiny little microscopic holes in it. So those holes are actually small enough to allow little molecules through, but not large molecules. So something like a mixture of sand and water, sand too big to go through them, sits at the top, and that will be our residue, whereas the water goes through because it's small enough, and that becomes our filtrate. So just remember those key bits about filtration. First separating technique, insoluble solid from a solution. The next one that we've got is crystallization. Now, crystallization is how we're actually going to separate a dissolved substance from a solution. Now, again, you should have done this, and I would guess you probably did an experiment using copper sulfate at this point, so a blue liquid that you made little blue crystals up here. So what we actually have is a water bath, first of all. You've got your evaporating dish sat in the top here, and that's your actual solution that we're going to be crystallizing. Down here, we've just got some water that we then heat with our Bunsen burner. Now, the reason that we use a water bath rather than just whacking a Bunsen burner straight onto the evaporating dish is for the simple fact that it needs to be gently heated. If you heat the evaporating dish, you evaporate off a lot of the solution really quick, but then you're also going to end up with this really pathetic end product, because it's going to be this very fine powder that if you don't turn your Bunsen burner off quick enough, it spits everywhere anyway. So we sit it on top of the beaker of water to create a nice little water bath, and that means it's going to be nice and gentle. We keep heating it until it becomes saturated. So we've evaporated off enough of our actual liquid to make it nice and saturated so that you can start to see crystals begin to form. At that point, what you do is you're going to turn off the Bunsen burner and then leave it to then finish crystallizing. The whole idea behind this saturated solution is that no more solute can dissolve at that temperature. So what we then find is as the solution cools down, once you turned your Bunsen burner off, the solubility of the solute will decrease and more crystals will then form. So what you end up with after a little while are all these lovely crystals that you can then separate out. And the way we separate that is by filtration, and then you just dry them in a warm oven, or you can just pat it dry with a bit of filter paper. So make sure you do know how to carry out crystallization as well. Our next separating technique is simple distillation. So with our simple distillation then, we start off with our round bottom flask here, which is connected into this bit of equipment, which is called a condenser. Now, the way the condenser works is that we have cold water come in at the bottom here, and it flows all the way around up to the top and leaves at the top here. So that the gas that we're making over here comes down the center and is cooled, so it condenses in here and then just drips out at the bottom. Now, the whole idea of using simple distillation here is just to separate the solvent from the solution. Now, the whole idea behind this is all relying on the boiling point. So the solvent must have a lower boiling point than the solute in order to separate it out. So the solvent will evaporate, pass down the condenser where it condenses, and then you collect it in a tube at the end. The other kind of distillation we've got is fractional distillation. There it is. So this one is a little bit more complex, and we're going to look at this again when we come back to paper 2 in chemistry, where we look at our crude oil. But the principle is about the same. We start off with a round bottom flask with our mixture. In this case, it's an ethanol water mixture. And then as we heat it up, then they pass up the fractionating column, we condense it down and collect it. Now, we use fractional distillation to separate 2 or more substances from a mixture in the liquid state. Now, what we actually find is that each substance must have a different boiling point. And the reason for that is that if they all had the same boiling point, they'd all evaporate at the same point, and therefore they would all collect at the other end. It wouldn't work. So ethanol and water have 2 very different boiling points. Ethanol is 78, I think, and water 100. So make sure you do know water boils at 100 degrees, just in case. And that means ethanol is going to evaporate first, condense down, and collect on the other side. So we can separate the water and the ethanol. Do remember the name of the fractionating column as well. So sometimes they'll give you this diagram and say, what is X? And it's just a fractionating column. That's all they're looking for there. Our next separating technique is chromatography. So again, something you probably did in class. You probably did it back in Key Stage 3 as well. Now, 2 different ways that you could have done this one in class, depending on how much you've actually got in terms of cash in your school. Most likely with a bit of filter paper, because schools don't have money. If not, you would have done the rather flashy thin layer chromatography, which is a plastic or glass plate with this powder stuck to the surface. The way it works though, pretty much the same. What we have is our chromatography paper or plate here. You put a little dot of your sample at the bottom, okay, but not the very bottom. It's got to be a little way up, and it's got to be above the solvent line there. Then what we do is we stand it in the solvent and we leave it. So what's going to happen is the solvent is actually going to be drawn up our paper or our plate, and as it does so, it drags the chemicals in our sample up as well. We'll stop it before it reaches the very top, okay? You don't want it going off the top, you want it just to move up the plate. And as it does so, the different sizes of those chemicals are going to move at different rates. So they're going to separate out from one another. One thing they could ask you to calculate with this is something called the RF value. So the RF value, quite simply, is the distance traveled by the substance divided by the distance traveled by the solvent. So if you're asked to calculate that, number one, take a ruler into the exam, otherwise it's not going to go well. Then place your ruler on the bottom line here and measure how far to the center of the first spot. Then you will also need to do that for any of the other spots they're asking you to do. And from there, to wherever the top of the solvent line is. So it doesn't go right to the very top of the plate or the paper, just goes to the line that the solvent reached. Once you've got that, distance travelled by the substance divided by distance travelled by the solvent, and then you just divide them. Nice and simple. Do remember that when we're talking about chromatography, then we actually have a couple of different terms that we need to know. We've got the stationary phase and we've got the mobile phase. So stationary is the one that doesn't move, hence stationary. So it's the paper, it's the actual powder on the plate, whatever that is that's not moving, that's your stationary phase. The mobile phase is the solvent that's moving it up there. Another kind of chromatography is gas chromatography. So slightly different in this one. We inject our sample over here and we've got this carrier gas. So we turn it into basically a vapor and we push it through this coil, which is packed full of a powder. So that means that the particles are going to travel through slower depending on their size. And then as they come out the other side, they're picked up by this detector and we get a chromatogram on the screen of the computer there. So just by passing it through the gas chromatography equipment, we then generate this little image of peaks on the computer screen so we can identify what's actually in there. Those are the different separating techniques that they could ask you about. One of the questions that they have asked previously, and it was a 6-marker, was going into looking at 3 different substances and you had to explain how to separate them out. So what you need to do is have a look. Are they soluble? Are they insoluble? What are their boiling points? Those kind of features in order to identify which of the techniques we've just discussed is best to separate them out. And if they actually give you 3 samples and say, explain how we would get pure samples of each of them, then just start with the first one, explain how to get that one. Then you do the same with the second and then with the third. What they're looking for is a description of how to do it properly. So you need to name the technique and then explain how to do it. So this isn't just a case of sample A, I would use chromatography, sample B, I would do this. You've got to take it in a logical order and actually explain how each of those processes works. Now, in terms of chromatography, it's actually a really useful one for working out whether we have a pure or impure substance. Because when we actually look at the chromatogram, then what we'll end up with are these little spots. So what we have, this one, we've got 3 different spots on there. That's an impure substance because we've got 3 different chemicals. They've made 3 different areas. Whereas this one, there's only 1 spot, it's a pure substance. So that's a nice simple way that we can use chromatography to work out whether something is pure or not. If we want to be comparing TLC, so thin layer chromatography, and paper chromatography, then thin layer chromatography is better. And the reason that TLC is better than paper chromatography, it's quicker, first of all. It's more sensitive to the smaller samples, so we can use a much smaller sample there. It can actually use a larger range of stationary phases and solvents, and a single spot from that TLC plate, once we've separated it out, can then be taken and used in gas chromatography to actually identify it. So what we can do there is use those to then not only separate out these chemicals, but then use a second process to identify what they actually are. In terms of our gas chromatograms, then it looks slightly different. So we end up with these little peaks on an actual screen. So really bad drawing, looks like a couple of ears. But you end up with these peaks and we can identify what those are by comparing to known samples. So wherever the peaks occur, based on their travel time, we can then identify those samples as well. Do remember that when we're talking about these separating techniques, it's not a case of just a single one. You will actually potentially have to combine a couple to get the pure samples. So don't worry if you just need to go through one thing at a time and then say, okay, I've separated out substance A, but now I've still got B and C together. What do I do now? Then just take one step at a time, remember. So those are our separating techniques. And as I've said, it has been a 6-marker in the past. There's a lot you can write about it, so there's a good chance of that. In terms of the next thing we need to look at, we need to have a look at some properties of different chemical substances. And the first one of these is metals and non-metals. Hopefully we do remember on the periodic table that metals are on the left-hand side and the non-metals are on the right-hand side. Now, physical properties are any characteristic that we can observe or measure. And a couple of key ones that we should know here are malleable, which basically means that we can bend it without it shattering, which is a key property of those metals there. Whereas something that's non-metal tends to be brittle, so that if you were to try and bend it, it just shatters and it's brittle, okay? The other one is ductile, which means that you can pull it into these thin wires. Again, brilliant property of our metal there. Whereas a non-ductile material, if you pull on it, it just snaps. The other kind of property we can talk about are chemical properties. So these are the characteristics that we can only determine by studying the chemical reactions. Now, a couple of the key ones we will need to know here: metals and non-metals will react with oxygen in order to form something called an oxide. Name's quite obvious there as to why. And if we dissolve it in water, those metal oxides produce alkaline solutions, whereas the non-metal oxides produce acidic solutions. So that's one way you can actually work out whether it's a metal or a non-metal, is based on the type of solution we make when we dissolve it. If we then think about that bit where you got the boundary on the periodic table, and I don't have periodic table with me, so apologies, then on that right hand side you end up with that little kind of step that you end up going down between the metals on the left and the non-metals on the right there. But some of those elements along that little step line actually have properties of both metals and non-metals. They're kind of floating between the two. The other key things we need to know about on the periodic table are the periods and the groups. So periods, horizontal rows going across, and the groups are the vertical columns going up and down. Any of the elements that are in a particular group will have similar chemical properties, and that's all down to the arrangement of the electrons there. Do remember, if they ask you about periods, then don't miss the first period. So period 1 on the periodic table is right at the very top with hydrogen and helium in it only. So when you glance at the left-hand side, you see lithium and you think, oh, that's 1. Lithium is actually in the second period. So go really careful on that one, because it's a really easy way to just throw away quite a nice easy mark. If we now come on to have a little look at how we actually draw the electronic structures, then as we said earlier, in our atom, then we've got the electrons in the shells around the nucleus. We need to know how to actually draw those for the first 20 elements according to the specification. There are 4 rules to remember to be able to do this. First one is that the first shell can hold a maximum of 2 electrons. The second shell can hold up to 8 electrons. The third shell up to 8 electrons. And the fourth shell can hold up to 18 electrons. So what we've got there then are the 4 rules that allow you to draw any of the first 20. So what we then need to do then is understand that when we talk about the outermost shell, okay, or the outer shell, then that's the one around the furthest edge that's got electrons in it. So anytime they talk about the outer shell, then it's the one that's furthest away from the nucleus. Once you've actually drawn your electronic configuration, then what we end up with is the ability to write down the structure. So if we've drawn, let's draw lithium very quickly. So lithium's got 3 electrons, 2 go in the first and then 1 in the next. So that when you actually come to write its configuration, it's just 2, or dot 1. So what we actually have here is the 2 numbers, which tells us the number of periods. So it's in period 2. The last number, that 1, tells us it's in group 1. And if we were to add the 2 and the 1 together, we have 3, and that tells us the atomic number. So there's 3 things that we can actually work out just by looking at the electronic structure there. As we mentioned earlier, we've got these things called ions, which are charged particles. So the reason they're charged particles is because electrons have moved. Don't say protons have moved or neutrons have moved. They don't, okay? The only thing you need to know about for our ions is electrons have moved. They've either gained or lost electrons. So what we actually find is our metals on the left-hand side of the periodic table, they lose electrons and therefore become positive ions. whereas the non-metal atoms on the right-hand side of the periodic table gain electrons and become negative ions. Once we've actually generated these ions, then we've got some are positive, some are negative, and what you actually find is that they will then attract to each other in structures in this regular little repeating pattern where you end up with a positive next to a negative next to a positive and so on. And that's something called a giant ionic lattice. So you've got all of these positive and negative ions just in a neat little arrangement. That is a giant ionic lattice. They're all held in place by these things called ionic bonds. So if we've got a metal and a non-metal, it's ionic bonding first of all. And an ionic bond, quite simply, is a strong electrostatic force of attraction between oppositely charged ions. You need to be able to draw the dot and cross diagrams for these. So what we've got, lithium and fluorine. Okay, so metal, non-metal. We've got 3 electrons in lithium, 2 in the first shell, 1 in the outer shell, and fluorine has 9, so 2 in the first and 7 in the outer. So what actually happens when these form ions is this electron from lithium is transferred to fluorine. So as a result of that, then what we end up with is the lithium actually has lost an electron, so it's gained a positive charge, and our fluorine gains this electron and gets the negative charge. So when we actually draw it, you can see the lithium here has got the positive charge because we've lost 1 electron. So we've got 3 protons in it, but only 2 electrons. And our fluorine has gained that extra electron, which we must draw as the opposite, okay? So you've got to have a dot and cross. They're called dot and cross diagrams for a reason, folks. One must be dots, the other must be crosses. And that's so we can see where this extra electron came from. You then use your square brackets, and then don't forget the charges. So the key thing there is, number 1, dots for one, crosses for the other. Secondly, square brackets. And lastly, put your charges in there. If we were to have 2 electrons being lost, then it would have a +2 charge. Whereas if it was gaining 2 electrons, 2 minus. So quite simply, just the number of electrons moving tells you the actual charge on there. Hopefully, you can draw those ionic bonding diagrams now. The next one we're going to come on to is the second type of bonding, which is covalent bonding. So what we start off with are simple molecules, first of all. Now, your simple molecules are things like carbon dioxide and water, oxygen. They're little molecules, hence simple. They're made of only a few atoms. And what we actually find is that those atoms are held together by a covalent bond. Now, this will occur in non-metals. So where we've got non-metals joining together, it's covalent. And the covalent bond itself is a shared pair of electrons. So make sure you remember that phrase, shared pair of electrons. When we're actually drawing them, what we end up with is something like this. So this is methane. We've got carbon, which has 4 electrons in the outer shell, and hydrogen has 1. So all we've done is we've shared 1 electron of the hydrogen with 1 of the carbon. So we've got 1, 2, 3, 4 covalent bonds there. And that's all you need to do with the covalent bonding is share them between. Ionic is the transfer of electrons, and then the electrostatic force of attraction between the positive and the negative ions. Covalent, they share the pair of electrons each time. And do remember, covalent bonds are strong bonds as well. The next thing we need to consider is how we can actually model this, because it's all good and fine talking about all these different molecules and how the atoms all join together, but it's not easy to see because they're tiny. So we use these different types of models here. So the first one is something called a ball and stick model, which is, as the name suggests, kind of like balls joined together with sticks. And if you played with the little Molly Mod kits, the little plastic balls, the little plastic sticks that you stuck together in class, that's pretty much it. Limitations to this one, though, is that we're not actually using realistic sizes of atoms or bond lengths. So what we actually find there, we're massively exaggerating them. And secondly, it suggests that the electrons making that bond don't move. If you've got a rigid bit of plastic, it's saying it's stuck. Electrons move. In terms of another kind of formula that we could do is the displayed formula. So the displayed formula for methane just looks like that. So all we're doing is replacing our bonds with a single line. Downside of this one, it doesn't show us the 3D shape of the molecule. So each of these models that we use does still have a drawback here. When we're talking about covalent bonding, we do have giant covalent structures, which basically are made up of lots and lots of non-metal atoms joined by those covalent bonds in this regular repeating pattern called a giant lattice. And two really good examples of that is silica and diamond. Next thing we're looking at, polymers then. So when we're talking about a polymer, quite simply, this is a chemical that's made up of many alkene monomers joining together. And to do that, they need two conditions, which is high pressure and a catalyst. So in order to do that, that's something called addition polymerization. And again, we come back to that in C6. So this is something that there's a bit of overlap. And I just don't trust exam boards not to throw in a little bit about C6 in your first paper. So just look over your polymerization notes from C6 as well, just as a backup. If we actually come to look at these then, when we're looking at how we can draw these, then the first thing is learning their names. Now, if we start off with our monomer of ethene, then in order to turn that into the polymer, all we do is we write the word poly in front and stick the monomer in brackets. If they were to give you the actual polymer name and say it's polyethene and say what's the monomer, then all we need to do for that is write out the bit that was in brackets. It's just ethene. So that's pretty easy to work out the names of the polymer or the monomer. If you were asked to actually draw one of these as the displayed formula, there's our monomer. Whatever they give you as the monomer, it's the same process. And all we then need to do is put brackets around it, remove the double bond in the middle, and stick the bonds coming out the side. So all we've done there is we've removed the double bond in the middle, we've put brackets, extended these bonds out to show they're joining onto lots of them, and we've put a little N in the bottom corner to say there's a number of them, quite a few. Not going to put an exact number down. Now, that's pretty much as complex as our polymers get at this point. We do need to know that there are two kinds of polymers that we could encounter here: thermosoftening polymers or thermosetting polymers. Now, the thermosoftening polymers are the ones that don't have crosslinks. So they're basically like a load of little wavy lines together. So each of these is a polymer chain, and you can see they're not bonded together in any way, shape or form. So that means they can be really easily separated. And this would be in things like a carrier bag, for example. So when you put on it, stretches because they're just moving over each other. Whereas in our thermosetting polymer, then each of those polymer chains is actually held together by these things called crosslinks. So you can see we've got these bonds that are actually going between the polymer chains, and that means they're going to be more rigid. So that's like the plastic book boxes you probably have at school. They're made of the thermosetting polymer, so they're more rigid due to the cross-linking. If we consider our metals then, what they have is a very clear structure, and they used to ask you to describe the structure of a metals or the bonding in metals quite frequently. So when we have a look at it, this is the more common diagram that we draw. So you draw your positive metal ions and label them as positive metal ions. And then we've got these little dots around, which are delocalized electrons. So if they ask you to describe the bonding in a metal, draw that diagram. Positive metal ions, delocalized electrons, and just label those. Then all you've got to do is write one sentence to say that there's a force of attraction between the delocalized electrons and the positive metal ions, and that's metallic bonding. That used to be a 3-marker, so nice and easy for one diagram and one sentence there. When we think about our metals, all of them are solid at room temperature with the exception of mercury. And what we find is that these atoms in metals are arranged in a giant metallic lattice. So we've got metallic bonds in metals. Nice and straightforward for our final type of bonding here. What we have is the outer shell of our metal atom. The electrons from there are able to leave it, hence where we get these delocalized electrons from. And that's why the metals become a positive ion at that point. So because we've got the positive metal ion, the negative electrons that are delocalized, then they attract each other. Next thing, periodic table. So that thing that you probably love to hate by this point. The periodic table itself that we use today is based on the one that Mendeleev created. And what we actually had when he was creating it, he considered a range of evidence. First of all, the atomic weights of the known elements. Secondly, he looked at his knowledge of the chemical reactions of different elements and his knowledge of the physical properties. And then he put them into this very clear order that we see today. But he didn't have all of the elements back then. So every once in a while I get to one and think, well, this doesn't really fit there. It needs to go one step over. And so he actually moved it one step over and left these gaps in the periodic table. And that was for these elements that hadn't yet been discovered. So what he then also did was go on to say, this gap I've left here, that's going to be an element that when it's discovered is going to have the following properties. And he was actually pretty blooming good. So when we look at the properties he predicted, he was almost spot on for those. The other thing he did was he flipped tellurium and iodine, because when he looked at their properties, he thought these are going the other way around. And again, he was exactly right, because they didn't know about the atomic number in those days. They just had the atomic weights. So since we've actually come to understand atomic number, proves he was spot on with what he said. One other kind of key scientist we should know about here is the work of Ramsay. So Ramsay actually discovered elements that no one had even thought would exist. And the first element he discovered for that was argon. And the reason that no one thought that this element would exist is because it's one of the noble gases. Right on the right-hand side, we've got those group 0, okay, which are the noble gases. They're pretty unreactive. So that means no one really knew they did anything, so we didn't know they actually existed there. If we think about the periodic table, then there's a few key patterns that we should know. First of all, the elements are arranged in order of increasing atomic number. So hydrogen's 1, helium's 2, lithium 3, and you just keep counting up one at a time. Your atomic number is the number of protons in an atom. And remember, your number of protons is the same as the number of electrons in the atom. Your electronic structure is determined by the number of electrons, and that electronic structure then gives us the chemical properties. So they're all tied together. And if they were to ask you what you can work out about the electronic structure from something on the periodic table, then they're looking for number of protons, number of neutrons, number of electrons, how they're arranged, number of shells. Put all of that in, put the group number in, tell them what period it's in. All of that you can get from just that one little box on the periodic table. Next thing we're going to come on to is carbon. So carbon is kind of special because it has a range of different forms that it can take. And these things are called allotropes. Now, an allotrope is just the different form of the different form of an element in the same state, but with different atomic arrangements. Now, carbon itself is in group 4, okay, and that means it's got 4 electrons in its outer shell, which means it can form 4 covalent bonds. So what we actually find is carbon can either form them with other carbon atoms or with other atoms. So it's quite a versatile chemical as well. We need to know about 3 of these allotropes of carbon. So we've got diamond, graphite, and the buckyballs first of all. Now, diamond is the kind of triangle-shaped one. So you can always spot diamond with the triangle shape. Graphite is like a load of layers stacked one on top of the other. And the buckyball is basically a ball, as the name suggests. If we think about diamond, first of all, then this is a giant covalent structure. So between each and every carbon atom, we can see these lines, which are covalent bonds. Each of those carbons is joined onto 4 others in diamond. So because of that, all of the electrons are involved in bonding. So that means that diamond will not conduct electricity because there are no delocalized electrons. However, diamond does have a really high melting point because there are many covalent bonds in its structure which require a lot of energy to break. So if you are ever asked a question to do with bonding and structures as to why something has a high melting point, it has many bonds, ionic, covalent, whichever one it may be, which require a lot of energy to break. If you're asked why something does conduct electricity, it has delocalized electrons or it has charged ions that are free to move. If why it doesn't conduct electricity, it has no delocalized electrons. So there's a few little key phrases that you can just kind of throw in there just to get those marks quite easily. If we consider graphite then, our next one here, then what we actually have is another giant covalent structure, but each carbon is joined onto 3 others in this case. So we've got 1 spare electron kicking around in each carbon atom. That electron then becomes delocalized, which means that graphite will conduct electricity because it has a delocalized electron. It still has a high melting point because we've got lots of covalent bonds that need lots of energy to break them, but it also has another property of being slippery. So each of these layers we can see here has weak forces between them. So you can see little dotty lines there. Now, those weak forces between the layers are really easily overcome, so they can just slide over each other, hence why graphite is slippery and it leaves a mark when you're using a pencil. One other is graphene. So we can see graphite. Graphene is pretty much just a single layer of graphite. Now, that one is extremely strong, it can conduct electricity, and it's almost transparent. So graphene is one of these chemicals that actually in the future could be really quite a game changer in the world of technology. So I know in the past they used that as a question on a mobile phone, where apparently they had this battery that would charge up almost instantly on your mobile phones and therefore give you massive charge for a long period of time with instant tap charge and 100%. Watch out for that. It's only talking about the fact it can conduct electricity, it's extremely strong, any of those key properties we've talked about. Don't be thrown by weird context they put things in. Once we've actually got the graphite and the graphene, then we can go one step further and create something called a fullerene. Now, fullerenes are basically the carbon allotropes that we've made into tubes or balls. So this is where our little buckyball comes in. Now, the buckyball is 60 carbon atoms, all arranged in a sphere shape, and they're quite exciting as a chemical as well. Because they're basically like a cage, we can put things inside like drugs and use them as a drug delivery system. We can also use them as lubricants as well, so quite a range of uses there. In terms of the nanotubes, then all we've done is we've just wrapped up a bit of graphene basically into a tube, and these are then incredibly strong. So we use them to reinforce tennis rackets, for example. So make sure you do know those different carbon allotropes. When we think about changing states of chemicals then, when we're changing from solids to liquids, we're breaking some bonds. But when we change it from a liquid to a gas, we break all the other bonds. So if they ever are asking about how changes of state are related to bonds, then solid to liquid, some bonds break, liquid to gas, the remaining ones break. And what we actually find is that the stronger the bond, or the more of them there are, then the greater the amount of energy we've got to transfer from the surroundings to actually break them. So what we find is a substance that's got a high melting point has a lot of strong bonds in the solid state, okay? If we want to explain properties like being brittle or malleable, then this is all about how easily the atoms and the particles can change their position within that lattice. So what we actually find is that those that are malleable, they can move around each other quite easily, so metals. Whereas those that are brittle, they can't. So when you actually apply the force, rather than sliding over each other, they just snap instead. If we think about the giant covalent structures then, these ones tend to actually be quite brittle. So what we find is the non-metals tend to be brittle in their nature, because when we apply a large enough force, many covalent bonds are breaking at the same time and it just snaps. Same idea with the ionic compounds, except it's many ionic bonds that break at the same time. And if we think about simple molecules and polymers, then they tend to be quite brittle as well, okay? If we think about the conducting property then, if a substance has a charged particle that is free to move, whether that be ions or electrons, then it will conduct electricity. So make sure that you do remember that key part there. So what we find, metals will conduct electricity in solid or liquid state because they've got delocalized electrons. Ionic compounds, they've got the ions, which are charged particles that are free to move when they're either molten or dissolved. So they won't conduct as a solid, but they will conduct when they're molten or dissolved. And then finally, your simple molecules, polymers, and the giant covalents don't conduct electricity they've got no charged particles, and they've got no delocalized electrons. So just remember that you can explain those quite nicely. For those of you doing GCSE chemistry, you need to know about nanoparticles. So a nanoparticle is just one that's between 1 nanometer and 100 nanometers across. And do remember that when we talk about a nanometer, that's 1 times 10 to the minus 9 meters. If we talk about a nanoparticulate, that's just a material made from nanoparticles. And what we actually find is that when we compare the properties of an individual nanoparticle to when we've got lots of them together, then their properties actually vary. So they do get a bit different. So a good example of that is titanium dioxide, which when it's in a bulk quantity is actually white, but when we have just a single particle, it's transparent. So we've got a different property there based on if it's on its own or as a bulk lot. Do remember that with these nanoparticles, they can be very useful in a whole range of things. Everything from paints, cosmetics, sunscreen, self-cleaning windows, lots and lots of things there. So make sure you know at least 3 ways that we can use nanoparticles. One of the other key things they could ask you about them is why they're useful as a catalyst. And the key idea there is they've got a very large surface area to volume ratio. We do have to consider some of the risks associated with nanoparticles. And the key thing here is they're really tiny, which means you could breathe them in or absorb them into the skin or your cells. Now, we don't know what the long-term effects of that may be. They've just not been around that long. So hoping nothing, but we don't know. Also, remember, they take a long time to break down in the environment, so we don't know the long-term environmental impacts of it. And if we're talking about using to coat windows, then toxic substances may also stick to their surface as well. So we may see an accumulation of those. So that's C2 done. Last one is C3. So the first thing we need to know about C3 then is how to write a formula. If we're talking about a metal, it's the empirical formula, Mg. Done. You don't need to worry about how many of them there are, just the actual formula. Next one is to actually consider the group 0 on that far right hand side, our noble gases. Those exist as an individual atom. So helium, neon, argon, krypton, xenon, radon, all of them, you just write the symbol. Nothing else, they only exist as that one atom on its own because they're unreactive, they don't join. If you think about group 7, the halogens, this is where you need to be really careful, and this is where people throw away marks every single year by forgetting this one fact, which is that group 7 are diatomic, okay? Di meaning 2 atomic atoms. So they go around as 2 joined together. So Cl2, F2, Br2, I2, At2. Remember that little 2. And when we're writing it, can we also make sure that we can write a chemical formula properly? Because you will lose marks if you do weird things. When we're putting the number of our atoms, bottom right, if you don't put it there, if you do weird things like this, so if you put it as a big number, wrong, put it up in the top right, wrong. Only place you'll get it is in the bottom right corner. So make sure that's there. And do remember that, because otherwise, anytime you're using a halogen in any balancing equation, you're going to get it wrong if you haven't put that little 2 there first of all. When we're writing a molecular formula, that's going to tell us the symbols for the elements and how many of each element there are. So CO2 is made of 1 carbon and 2 oxygens. So you can work those bits of info out. When we then come on to have a little look at some of the charges that we get with some of these chemicals, there's a few key ones that you need to know. So hydrogen, when that forms an ion, it's always H+, a +1 charge. Anything in group 1 is a +1 charge, group 2, +2 charge, group 3, +3 charge. You may notice a pattern here. So the group number, 1, 2, 3, that tells you the number of positive charges. If we then go across to the right-hand side to groups 5, 6, and 7, then group 5 have a -3 charge, group 6 a -2 charge, and group 7 a -1 charge. So all you need to remember are those, and you can work out the charge on any of those ions. That block in the middle of the periodic table, the transition metals, they usually have a +2 charge, but sometimes they've got a +3. There are exceptions. But you can always work that out from the information in brackets. When they give you a Roman numeral in brackets with a transition metal, that just tells you the charge there. There are 5 compound ions that you should know off by heart here. So a compound ion is an ion that contains more than one element. So we've got ammonium, which is NH4+, hydroxide OH-, nitrate NO3-, carbonate CO3 2-, and sulfate SO4 2-. So do remember those 5 because they're going to be really important in helping you to then put together ionic formulae properly. So when we're writing ionic formulae, the key thing is that your positive and negative charges must be the same. So when we've got something like potassium chloride, it's nice and easy. Potassium, single positive, chloride, single negative. So that, quite simply, forms KCl. Whereas if we were to have magnesium chloride, magnesium's in group 2, so it's got a 2+ charge on it. Then what we've got, 2 positive charges here, 1 negative charge here, which means that when we actually write the chemical formula, 2 chlorines will be joining to each magnesium, because that then gives us the 2 negative charges to cancel out the 2 positive charges. So just remember, those charges must balance in order to get it right. When we think about conservation of mass, one very simple law you need to know, which is atoms cannot be created or destroyed. So the only thing we can do is just change how they join together in a reaction. So what we also know is that the total mass of our reactants must be the same as the total mass of our products. And we can prove that if we use a closed reaction system, because when you carry out the reaction, nothing can enter or leave, and therefore the mass at the beginning will be the same as the mass at the end. When we come to write equations then, and I'm not going to spend a massive amount of time on these because this is something that you're hopefully good at. If not, there are videos on my channel you can have a little look at here. Then what we've got, word equation, first of all. You've got to write the full name. Do not be lazy in the exam, and if you're asked to write a word equation for a particular reaction that's got carbon dioxide, don't write CO2. It's not a word, it's wrong. So always write the full names in a word equation. The balanced symbol equation is going to be where you're using the chemical symbols. And then remember, just make sure that you've got the same number of each atom on each side. And as I say, if you're not sure on balancing, have a look at the video on my channel that will take you through how to do that. The other bit of information we can have in our chemical equation are the state symbols, which just tell us the physical state of our substance in the reaction. So an S in brackets is a solid, L in brackets is a liquid, a G in brackets is a gas, and an AQ in brackets tells us it's an aqueous solution. And general rule of thumb is that if you're talking metals, they're going to be solids. If we're talking about water, that will be your liquid. And obviously you've got your oxygen, your hydrogens, carbon dioxides that are gases. Other than that, if you're not sure, go with aqueous solution, so the AQ in brackets. For those of you doing the higher tier, you do need to know about half equations and ionic equations. So half equations are models for the change that happens to one of the reactants in a chemical equation. So what we actually find is you're only focusing on a single one of the reactants. So for example, you might be looking at sodium atoms losing an electron to become a sodium ion. So what we'd actually write as our half equation for that would only be focused on our sodium. So all we do, we start off with a sodium atom, and then we make a sodium ion and an electron. So E- is an electron there. You could obviously do the same for the other side of that one. If it was sodium chloride we were looking at, you could do the same with the chlorine. So Cl2 plus 2E- makes 2Cl-. When we talk about an ionic equation then quite simply what we need to do here is look at all of the ions that are present. So what we actually find here is you look at the equation they've given you, which will be a balanced symbol equation, and then you're going to split them into the individual ions. So if you had hydrochloric acid and sodium hydroxide making sodium chloride and water, then you would split your hydrochloric acid into hydrogen ions, H+, and chloride ions, Cl-, and you do that for each of them. Now, what you'll find is when you do that, there are some ions that don't change on the left compared to the right. And those are the ones we refer to as spectator ions. They're merely sitting back, having a little look at it, not really taking part in anything. and we don't really care about them when we come to write our ionic equation. So identify the things that don't change and leave them out. All you need to include when you're writing your net ionic equation are those that are changing from the left to the right-hand side. So you leave out the spectator ions. That's the key thing. And the most likely scenario that they will use here is in a precipitation reaction. Still, for the higher tier, you need to know about the mole. So the one that a lot of you really just groan at as soon as I say that. When we're talking about a mole, then it's the amount of a substance that contains the same number of entities, which could be atoms, ions, or molecules, as there are atoms in 12 grams of carbon-12. So the unit for it is mol, M-O-L. And the way we're actually going to work out the number of entities is by using something called the Avogadro constant. So that quite simply tells us a number, and that is 6.02 times 10 to the power 23. And all we need to do to work out the number of entities in any number of moles of any substance is 6.02 times 10 to the 23 times however many moles it was. If it was 5, it's 5 times that. If it was 10, 10 times that. So nice, easy one there. When we talk about molar mass, that's the mass in grams of 1 mole of any substance. So the way you actually work this out, back to the periodic table, work out the relative formula mass, okay? And that then tells you the molar mass because it's only in 1 mole. And the units for that are grams per mole. So if you're asked to work out the molar mass of sucrose, for example, which is C12H22O11, then all you do, carbon has an atomic mass of 12, hydrogen is 1, oxygen is 16. So 12 times 12 plus 22 times 1 plus 11 times 16 gives us 342 grams per mole. That's the molar mass. Even if you hate everything else about mole calculations, work that out first and write it down, because you are going to get at least 1 mark for just adding. So we can all add, we can all do that. So you can do that first bit. The next thing with our mole calculations is you need to know that the mass in grams is the molar mass times the amount in moles. Learn that, because they're not going to give it to you. So make sure you know that, because you can then use it. So that when they've given you a question that tells you the mass in grams of one particular chemical, you've worked out its molar mass, then all you need to do is use that equation to work out the number of moles. And all you need to do for that is the mass in grams divided by the molar mass, and you've got the amount in moles. So you do that for your first chemical. Then you look at your balanced equation. It will tell you how many moles of each react together, or how many moles of this one form that one. And all we're then going to do is make sure they stay in the same proportions. So if 1 mole makes 2 moles, but you have 3 that you've worked out, it's going to make 6 because it's twice as much. So just apply that same proportion, and then you've got the amount in moles of your other chemical, times that by the molar mass of that one, you've got the mass in grams. So you can work through it. There's a video on my channel that will take you through that one, because obviously not easy just to try and explain it to you now, but you can at least get 1 mark just for doing molar masses, which is just adding. You can all do that if nothing else. When we're talking about limiting reactants, these are reactants present in any amount less than they need to react completely with the other reactant, okay? So they're the ones that are going to bring that reaction to a stop. If we had something in excess, then that means we've got more than we need to bring the reaction to a completion. So that's the one we've got leftovers at the end. So the limiting reactant is going to determine the amount of product we make. This is now back for everyone combined, and the chemistry, there we go, and higher and foundation. We need to know about exothermic and endothermic reactions. So exothermic, first of all, this is where the temperature of the reaction mixture will increase because heat's being given out to the surroundings. 2 good examples of that are combustion and neutralization. Endothermic reactions, it's the opposite. They have a reaction where the temperature will decrease, and that's because heat's being taken in from the surroundings to carry it out. Good example of that one is good old photosynthesis again. Other ones that will also be endothermic but don't show that temperature decrease are electrolysis and thermal decomposition. And the reason for that is we're taking energy in to break down substances. What we actually find then is that during any chemical reaction, then energy is being transferred. So from the surroundings, first of all, to break bonds in the reactants, so we've got our separate atoms, and then energy gets transferred back to the surroundings as those reacting particles form bonds. So energy goes in to break the bonds, it's given out as new bonds are made. And what we can do with that information is we can create something called a reaction profile. Now, a reaction profile is just a fancy way of saying we're drawing a little sort of chart to show how energy changes in a reaction. So the horizontal lines are representing the amount of energy in the reactants and the products. And then we've got a little peaky bit, that's going to be our activation energy. And then we've obviously got the difference, it's the energy change. So they're the key bits we've got here. So just to show you what I mean, this is it. Okay, so this is a reaction profile. So we've got the energy in our reactants, the energy in our products, and then we've got the energy change is the difference between them. And on the other side, same thing, except we can see the reactants have more energy than the products. And that little humpy bit there, that's the activation energy. So that's the energy we have to put in order to make the reaction take place in the first instance. When we actually look at that activation energy then, if we don't put enough energy in to get to that point, the reaction just doesn't take place. So every reaction has an activation energy. It's just that some of them, it's so low, room temperature is enough to get them over here. If they ask you to draw a reaction profile, just remember that the endothermic reaction, this is the one where we're going to have the reactants lower and the products higher. Whereas an exothermic reaction, reactants higher, products lower. So just remember that one for those two. If you're doing the higher tier, you do need to know how to calculate bond energies and energy changes. Now, the bond energy is just the energy we need to break 1 mole of any particular bond, and they will give you a table of all these different bonds and the energy that you need to break them. So all you need to do to work this out is look at your reactants, look at all the different bonds involved, and add it all up. Do the same for the products, and then you're just going to subtract. So all you're going to work out there is the difference between the energy in your bonds in the reactants and the bonds in your products. If you end up with a negative sign, then it's an exothermic reaction. If it's a positive sign, it's an endothermic reaction. So again, I've got a video on the channel to take you through that in more detail. Next thing we're coming on to is for everyone again, which is redox reactions. When we talk about a redox reaction, then this is where we've got reduction and oxidation happening at the same time. In simple terms, reduction is the loss of oxygen and oxidation is the gain of oxygen. So what we actually find is that whatever is gaining oxygen is being oxidized and is known as the reducing agent. A little bit weird, I know, but it is. Whereas the one that's losing oxygen is reduced and is called the oxidizing agent. So because they're happening at the same time in a reaction, it's redox. If you're doing the higher tier, then you will need to know this in terms of electrons. And the easy way to remember that is oil rig. So oxidation is the loss of electrons and reduction is the gain of electrons. So if you remember that, you can explain it in terms of electrons on the higher tier. Just remember that when we're looking at this, all you're looking at is, are those particular atoms gaining or losing electrons to form their ions? And that's going to then tell you whether it's a reduction or an oxidation. Everyone again, so higher, foundation, combined, chemistry. Next thing we need to know is pH scale and neutralization. Hopefully our knowledge from year 7 is still there and we do know acids, alkalis and neutrals. So first of all, an acid is a pH of less than 7, so pH 1 to 6. And these are the ones that will release hydrogen ions when they're dissolved in water. So with universal indicator, they're the ones that are reds, orange, yellows, those colours. Neutral is pH 7 and it's a green colour with universal indicator. And our alkalis, our pH is 8 to 14 and they're the blues and the purples with UI. What we find is that if we've got a base that can dissolve in water, it's an alkali, okay? And they release hydroxide ions, which are OH minus when they're dissolved in water. The way you've probably measured pH in school is with the universal indicator solution, and then you'd have sat there trying to stare at that silly little bit of card going, is it 3, is it 4, is it 5? Have it a good guess. Universal indicator solution isn't the most accurate. So if they ask you how you could improve an experiment using universal indicator, just use a pH meter, which is basically a little digital probe. You stick it in there, you push a little button, and it tells you on the screen, this is pH 6.2. Nice and easy. What we can then do is make it more accurate by using that pH meter. Type of reaction that you would have looked at is neutralization. And again, year 7 work hopefully coming back to our minds at this point, which is the reaction between an acid and a base or an alkali to form a salt and water. So acid plus base makes a salt plus water. So acids contain hydrogen ions, H+, alkalis, OH-, hydroxide ions, and they're going to react to make our water, H2O. The salt is going to be made of whatever else was present. So if we had something like hydrochloric acid and sodium hydroxide, then it will be sodium chloride. So the ending of our salt always comes from the name of the acid. 4 acids you need to know: hydrochloric, sulfuric, nitric, and phosphoric. So hydrochloric acid always makes a chloride, sulfuric acid makes a sulfate, nitric acid makes a nitrate, and phosphoric acid makes a phosphate. First part of the name is whatever metal name it was. So look at the metal, write it down, and then look at the acid and give it the ending. You'll get your salt name every single time then. If we think about another reaction, which are the carbonates and acid, then what we actually find is a metal carbonate plus acid makes a salt, water, and carbon dioxide. So most carbonates are insoluble in water. The ones that are soluble are group 1 carbonates and ammonium carbonate. Because they're making carbon dioxide, this opens up the possibility for them to ask you how you can test for carbon dioxide. And that's where you're going to bubble the gas through lime water, and it goes from colourless to cloudy. Don't write clear, transparent, see-through, or any of those other weird words. Colourless is the key phrase to start with, and then it's cloudy. If we had a metal and an acid, then we make a salt and hydrogen. Gas test number 2, how we test for hydrogen. Lit splint makes a squeaky pop sound. Do remember to say the splint is lit though. Those of you doing higher tier need to be able to talk about concentration first of all. So when we're talking about a solution, then that's a solute dissolved in a solvent, as we've already said. And the greater the amount of solute within that solvent, then the greater the concentration will be. So if we've got a dilute acid, then that's got a very low ratio of acid to the actual volume of solution, whereas a concentrated acid has a high ratio of acid to the volume of the solution. As we've already said, the acids release hydrogen ions in the solution. Now, the reason for that is the covalent bond is going to break between hydrogen and the other part of the acid molecule to make the hydrogen ion and a negative ion. When we're talking about acids, we've got concentration is 1, and strength is another key word we need to know. So when we're talking about the strength, this is all down to how ionized it is. So how many of those have actually been split. So a weak acid is one that's only partially ionized, so only some of the hydrogen ions have been released, whereas a strong acid is fully ionized. They've all been split. So don't mix up strength and concentration. They are 2 different phrases. If you happen to see this sign on your exam at all, let me just try and draw it on a bit clearer, then we've got something called a reversible reaction. So remember, this means it's a reversible reaction. That means it's not going to be going to completion, which means we've got a weak acid. So it's a nice, easy way to spot it. Whereas if you've just got a normal arrow, then it's a strong acid because it's going to completion. It's going to be fully ionized. When we then link these hydrogen ions into the actual pH, then when the hydrogen ion concentration increases by a factor of 10, the pH will decrease by 1. So hydrogen ions up by a factor of 10, pH down by 1. So a strong acid has a lower pH than a weak acid at the same concentration. They could ask you about titration at this point. because again, titration is one of those that spans across the two papers. And the way that we see this one is when we're looking at this idea of neutralization. So we could be given the idea of using a titration in order to actually make a neutral solution. And they give you this pH titration curve, which looks something like that. So we start off with it quite high, then we get this vertical point where it's being neutralized, and then it will decrease after that. So just look over that if you're not sure on titrations, just in case they're being mean and they put that into this paper rather than the other one. Right, back for everyone again, foundation, higher, combined chemistry for the last bit, which is electrolysis of all its different types. So electrolysis, quite simply, is where we're going to use an electric current to split a chemical. Pretty much all it is. Electricity, lysis, split stuff. So we're splitting things using electricity. In order to do this, three things are needed. First of all, we need a power pack as our electrical supply. Secondly, we're going to need an electrolyte, which is basically a compound in the liquid state or a solution. And finally, we need two electrodes, which will be made of either metal or graphite. Two keywords we should know first of all. Then what we actually have, cathode is the negative electrode and the anode is the positive electrode. Okay, so cathode is negative, anode is positive. What we then find is that as the electricity is flowing through, then any of the negative ions from our solution go to the anode, the positive electrode, because opposites attract. Whereas any of the positives go to the cathode, still opposites attracting. What we then find is you'll have the different substances forming on the two sides of your electrolysis tank. What we tend to use are things called inert electrodes, and inert just means it doesn't really react. And the reason for that is that then they last a long time. You don't really want to use something reactive, otherwise you're constantly wasting money having to change your electrodes out. So we usually use things like copper, platinum, or graphite because they're all pretty unreactive. When we actually come to look at our chemicals, then we could have something called a binary ionic compound. So binary, there's only two elements present. So that would be something like lead bromide. So what we'd find there, lead makes positive because it's metal. So that's then going to go over to our cathode and produce our lead. And then our anode is where the bromine is going to form, because bromine forms the negative bromide ions attracted to the positive electrode. What we then find is that as those ions reach the electrodes, they become discharged, which basically means they lose their charge and become atoms or molecules. So what we then have here are atoms or molecules being formed on the two sides of our electrolysis tank. As a result of that, then the concentration of the ions by the electrode is going to decrease, and then other ions move to replace them just through diffusion and convection. Do remember, though, that we can't do this with an ionic compound that's solid because nothing can move in the solid. They're just vibrating around that fixed point, remember. Next thing we need to consider is water in terms of electrolysis. So water is partially ionized. So we've got small concentrations of hydrogen and hydroxide ions. And what actually happens there, hydrogen ions are positive, so they're going to go to the cathode. Hydroxide ions are negative, they go to the anode. And as a result of that, we form hydrogen gas and oxygen gas as well. So just make sure you can talk about that. In terms of where we've got solutions, then there's obviously something mixed in with the actual water there. So what we find is hydrogen will always be produced at the cathode unless ions from a less reactive metal are present. In that situation, that metal is going to be produced. If, however, we've got the anode, then we'll make oxygen there unless ions from an element in group 7 are made, or we've got a high enough concentration of them, okay? So oxygen at the anode unless we've got group 7, in which case we make the group 7. So it's quite easy to work out what we're making, hydrogen at the cathode or a less reactive metal, and then at our anode, oxygen or a group 7, depending on what's present. So you should be able to work out what's what in that scenario. One thing that we can actually use this for is electroplating. So what you'll find is that quite common these days are things like white gold jewellery. Now, all that's happened there is we've just put a plating of a different metal on the surface of the gold, which is why you have to have it replated frequently, because it rubs down and you get the gold coming through again. So electroplating is going to use non-inert electrodes. So these are actually ones we're selecting because they change. So the cathode is what we want to coat, the anode is what we want to coat it with, and our electrolyte is a solution containing ions of that coating metal. So what actually happens as we turn our current on is that the metal ions from our electrolyte get discharged onto the surface of our object and it sticks to it. So we've created a coating around there. So the metal ions then leave the anode to replace those discharged metal ions, and eventually the anode gets used up because obviously we're transferring it from the anode through the solution to plate onto something else. So hopefully that all makes sense on the electroplating. The last way that we can use this is in purification, and the most common one they give you here is of copper. So when we extract copper from the ground, we'll learn about in our next chemistry paper, then it's not pure. So what we actually have to do there is purify it to use it in things like the wiring, our plugs and so forth. In this instance, the anode is impure copper, the cathode is pure copper, and our electrolyte is copper sulfate solution. So what we see happening here is the current's flowing through. The cathode gains copper atoms and will increase in mass because they're going over there. The anode will lose the copper atoms and therefore the mass will decrease. And then at the bottom of the tank, you end up with this sludge, which are all of the impurities that we've then removed from our copper. That is all of C3 and therefore everything that you need to know about all of your chemistry for tomorrow, I hope. Hopefully this has been useful. And folks, seriously, just don't bother paying attention to the Muppets in the chat because, let's be honest, they'll lower the grade boundaries for you quite nicely. Obviously, this has been helpful, hopefully, and we will be doing this again for physics next week, whatever day that one is, Wednesday, I think, again. So feel free to join us again for that one. Hopefully, you are going to find that the exam tomorrow is okay. Do remember to read the questions as always and just try and answer every question. At the end of the day, if you don't write something, you've got zero chance of having a lucky guess. If you write something, there's at least a teeny tiny chance of getting a mark there. And especially don't leave tick boxes blank because that's just really irritating. So good luck for tomorrow and hopefully I'll see you again next week.